Assalamualaikum, good day. My name is Hazarul. Today, I will be presenting my report titled Neural Network Application in Cardiac Rhythm Analysis with comparative insights on one-dimension RNN and two-dimension performance in CPR and arrhythmia context. As illustrated by the graphic on this slide, on the left, we have the traditional one-dimension ECG waveform. On the right, we have two-dimension time frequency, which represents the future of deep learning diagnostics. So in this presentation, I will demonstrate how different neural network architecture optimize these two data formats to solve two very different clinical problems, managing the issue of cardiac arrest and the precision required for diagnostics. This report is based on a comparative review of two significant studies published in 2025 as references. The first is by Lee et al. The title is a comparative study of a convolutional neural network and recurrent neural network models for the analysis of cardiac arrest rhythm. And the second is ECG heartbeat classification using two-dimensional deep learning convolutional neural network. So together, these papers allows us to compare convolutional neural network CNN against recurrent neural networks RNNs, and evaluates the trade-off between one-dimension and two-dimension data processing. Let's begin with case study 1, extracting signal from the noise of cardiac arrest, which is the challenge of analyzing heart rhythms during active cardiac arrest. The clinical problem here is noise. During CPR, chest compression creates massive mechanical artifacts that obscure the heart's electrical signal. This forces paramedics to stop compression to check the rhythm, which is dangerous for the patient. So Lee et al. Utilized a data set of 508 ECG segments collected from cardiac arrest patients to test if AI could see through this noise. They compare a one-dimension CNN against a recurrent neural network RNN. So we can see in the chart, the one-dimension CNN in green achieved an accuracy of 89.8% in detecting shockable rhythms while chest compression were happening. So while the RNN in gray failed significantly, achieving only 54.5% accuracy. Why the difference? So the study found that RNN suffer from the gradient variation problems and struggle to isolate the signal from the artifact. In contrast, the one-dimension CNN was efficient at capturing local morphological patterns. Moving to case study 2, signal to image conversion for diagnostic precision. Now we shift our focus from noise resilience to diagnostic precision. Here the goal is to classify 5 distinct types of heartbeats found in arrhythmia database, including normal beats, bundle branch plots, and premature contraction. And the methodology proposed by the second journal is different. Instead of using raw one-dimensional signals, they employ a technique called CWT, continuous wave flight transform, which is the stage 1. We take the raw one-dimensional signal, and then stage 2 we transform it into a RGB scalogram. This is a scalogram. This image capture both time and frequency spectral data simultaneously. And the stage 3 is this image is fit into a T20 layers two-dimensional CNN. So the result were better by treating the ECG as an image. The model achieved an overall classification accuracy higher than one dimensions. To synthesize these findings, let's look at these operational metrics. On the left, for the two-dimension CNN, the interpretability via CRAD-CAM. One major advantage of the two-dimension approach is that we can generate heat maps. So this visualize exactly which parts of the heartbeat the AI is focusing on, confirming that the network learns physiological relevant features like the QRS complex, dispute trust with clinicians. So on the right, for the one dimension CNN, we see it impact on ROSC detection, return of spontaneous circulations. The one dimension CNN achieved 89.8% accuracy in detecting when a pulse returns during compressions. This is critical because it tells paramedics exactly when to stop CPR without unnecessary pauses. This slide summarizes the core conflict and the solution found in this report. The challenge is that the cardiovascular mortality is compounded by two factors. First, manual error during complex diagnosis and algorithmic failure during noisy events like CPR. So the comparative analysis reveals a split in the strategy. The first in CPR, so we need robustness. So here one dimension CNN is preferred. It processes raw data efficiently and acts as a shield against noise, maintaining 89.8% accuracy where other models uh, fail. In the second in diagnosis, so we need resolution. Here, two dimension CNN converting signals to scalograms, we achieve 99.59% accuracy, allowing for the detection of subtle spectral features that distinguish similar arrhythmias. In summary, this is a comparison table between one dimension and two dimension CNN in terms of uh, input data, primary strength, and best applications. So the future of AI in cardiac rhythm analysis likely lies in a stratified approach, meaning to say uh, it will utilizing efficient, robust in one-dimension architectures for real-time uh, emergency intervention and uh, high resolution for in one-dimension architecture for detailed clinical diagnostics. So this concludes my presentation on neural network application in cardiac rhythm analysis today. Thank you for your time. Bye bye.